An engine is similar to an air pump. Its job is to take outside air, compress it, mix it with fuel, ignite this mixture to create energy, get rid of exhaust gases, then continuously repeat the process. This cycle of intake, compression, power, and exhaust describes how a four-cycle engine works. On the intake stroke, air is sucked in through the carburetor where it is mixed with atomized fuel and then drawn into the cylinder through the intake valve. The piston compresses this air-fuel mixture until a spark from the spark plug ignites the air-fuel mixture and drives downward on the power stroke. As the piston comes back up the cylinder, it forces exhaust gases out the exhaust valve and repeats the intake process. Another air pump that works similar to this principle is our lungs. Our lungs breathe in oxygen, our body converts that to energy, fueling the cells in our body, then exhausts carbon dioxide when we exhale. The effects of altitude on an engine are very similar to the way altitude affects our body's ability to breathe. Air density decreases as we go higher in elevation, and we see how this affects the engine's ability to produce power. At sea level, there are plenty of air molecules available for the engine so that during the compression stroke, it can draw in enough volume of dense air to generate the required power. The same holds true for our lungs, where there are enough air molecules to easily perform respiratory function. For an airport with an elevation or density altitude of 5,000 feet, such as Denver, Colorado, the air is still relatively dense, but we find that physical activity leaves us winded trying to catch our breath. The reason is that the air is less dense. Thus, taking the same sized inhale as that at sea level, there is a lower density of air molecules entering our lungs, despite taking in the same volume of air. The same effect occurs with an engine's ability to draw in air. Operations at 5,000 feet have a noticeable effect on aircraft performance. As we climb higher to 10,000 feet, we feel the effects of altitude on engine performance, as less air molecules are available to be drawn into the engine to make power. The same is true for our lungs. We notice that breathing becomes more labored, or that we need to take deeper breaths to increase the amount of air molecules delivered to the lungs. By the time we reach 15,000 feet, our lungs struggle to inhale enough oxygen. This is why the FAA requires the use of supplemental oxygen above 14,000 feet and recommends its use at lower altitudes. Supplemental oxygen supplies dense concentration of air to the lungs so they continue to function as if at sea level. Around 15,000 feet, normally aspirated engines no longer produce enough power to go higher. This is because the air is not dense enough for the engine to compress the air and generate more power. Similar to how supplemental oxygen makes our lungs perform better, we can add turbocharging systems to engines. Turbochargers use the expelled exhaust gases from the cylinders to turn a turbine that compresses the incoming air, which in turn supplies dense compressed air to the cylinders. This compressed air allows the engine to have sea-level performance up to a predetermined altitude, known as the critical altitude. Once above the critical altitude, the engine gradually loses power in a fashion similar to other engines due to the lower density of air at high altitudes.